December 1943, RAF Bassingbourn, England. Every single day, the 8th Air Force was losing an average of 176 airmen over Europe. Not from enemy fire, not from flak, but from something far more insidious: mechanical failure. Engines seized mid-flight. Oil lines froze at 25,000 feet. Hydraulic systems failed on landing approaches. The bombers that made it back were so damaged they'd sit in hangars for months waiting for parts that would never come. And in the middle of this mechanical apocalypse stood a 34-year-old former auto mechanic from Detroit named Robert Miller, holding a wrench and staring at 3 B-17 flying fortresses that every engineer on base had declared unsalvageable. Within 6 weeks, Miller would do the impossible. He would cannibalize burned wreckage welding table frames and salvaged bolts to rebuild 3 operational engines from absolute scrap. Those 3 planes would fly 47 wounded men out of combat zones in a single night. The British High Command would call it a miracle. Miller would call it Tuesday. But here's what nobody knew. What Miller built wasn't just 3 engines. He built a blueprint that would revolutionize field maintenance across every theater of war, reducing mechanical casualties by 34%, and keeping hundreds of bombers in the sky when they should have been grounded forever. This is the story of how one man's refusal to accept the word impossible changed the entire trajectory of the air war over Europe. And it started with a problem so catastrophic, so absolutely devastating, that it threatened to ground the entire American bomber offensive before it could even begin. By late 1943, the Allied bombing campaign was hemorrhaging aircraft at an unsustainable rate. Everyone talks about the German fighters, the 88mm flak guns, the horrific losses over Schweinfurt and Regensburg. But the statistics tell a different story. For every B-17 shot down by the Luftwaffe, 2 more never made it off the ground. Mechanical failure. The Wright R-1820 Cyclone engines that powered these massive bombers were engineering marvels, 18 cylinders, 1 ton 200 horsepower each. But they were also temperamental beasts that demanded constant maintenance, specific parts and expertise that was in desperately short supply. The supply chain from the United States was a nightmare. Ships carrying spare parts were being sunk by U-boats. Critical components were being diverted to the Pacific theater. What made it to England was never enough. Bases across East Anglia had become graveyards of wounded bombers. Aircraft with 1 bad engine. Aircraft with damaged hydraulics. Aircraft missing carburetors, fuel pumps, magnetos. The math was brutal and simple. The 8th Air Force needed 300 operational bombers for a major raid. They had 742 aircraft on paper, but on any given morning only 180 were actually flyable. The rest sat in revetments waiting for parts, waiting for mechanics, waiting to die from neglect while their crews watched the sky and wondered if their friends would make it back. Engineers tried everything. They stripped parts from the most damaged aircraft to keep others flying a practice called robbing Peter to pay Paul that left them with even more unflyable hulks. They experimented with alternative alloys, jury-rigged repairs, desperate improvisations. Nothing worked. Or rather, nothing worked well enough. A patched fuel line might last 3 missions. A rebuilt carburetor might fail on takeoff. The stopgap solutions were killing crews. In November 1943 alone, 14 B-17s crashed on takeoff or landing due to mechanical failure. 76 men dead. Not from enemy action. From broken machinery. The psychological impact on the crews was devastating. Pilots trusted their aircraft with their lives. When that trust eroded, when men started eyeing their bombers with suspicion, wondering if the starboard engine would seize over the North Sea, the entire operation began to crack. Mission abort rates skyrocketed. Men developed stress disorders not from combat, but from mechanical anxiety. The British called it equipment fatigue syndrome. The Americans called it what it was, fear that their own planes would kill them. But moi thu sap thay doi, vì một người đàn ông không ai để ý, standing in a freezing maintenance hangar, At 400 hours, staring at 3 aircraft that represented everything wrong with the war effort. Robert Miller wasn't supposed to be in England. He was supposed to be in Detroit, building tanks on the Ford assembly line, exempted from military service due to a childhood bout of polio that left him with a slight limp. But Miller had a different idea. In March 1942, he walked into an Army recruitment office and lied about his medical history. He was 33 years old, too old for flight training, too damaged for infantry. But he could turn a wrench better than any man in Michigan. The recruiter took one look at his resume, 12 years at Ford, specializing in V8 engine overhauls, and signed him up on the spot. By December 1943, Technical Sergeant Robert Miller had been at RAF Bassingbourn for 8 months. He worked 18-hour shifts in a Quonset hut that barely kept out the English winter. His crew of 6 mechanics serviced an average of 8 B-17s per week. They changed oil, replaced spark plugs, patched hydraulic lines, did everything possible to keep the bombers flying. But it was never enough. The planes kept breaking. The parts kept not arriving. And Miller kept watching good aircraft that could still fight get cannibalized into uselessness because nobody could figure out how to make broken engines whole again. Miller had a reputation on base. He was quiet, methodical, obsessive about details. While other mechanics followed the technical manuals to the letter, Miller improvised. He'd swap parts between different engine models if the tolerances were close enough. He'd machine custom fittings on a lathe he'd rescued from a bombed-out factory in Cambridge. His commanding officer, Captain James Weatherby, tolerated these improvisations because they worked usually. But there were limits. The Army Air Forces had regulations, procedures, technical specifications written by engineers in Ohio who'd never seen combat. And those regulations said that certain repairs were impossible without factory parts. An engine with a cracked cylinder head grounded. An engine with a damaged crankshaft grounded. An engine missing its supercharger assembly grounded permanently. The book was clear, and the book was killing them. On December 15, 1943, 3 B-17Gs limped back to Bassingbourn after a raid on Bremen. One had taken flak through the No. 3 engine. Another had suffered complete oil pressure loss in the No. 2. The third had experienced catastrophic supercharger failure at 28,000 feet and barely made it back on 3 engines. All 3 aircraft were declared Category E beyond economical repair. They were to be stripped for parts and scrapped. Miller walked around those 3 bombers for 2 hours that afternoon, making notes, taking measurements, thinking. Each aircraft had 3 good engines and 1 destroyed engine. But the destroyed engines weren't destroyed in the same ways. The flak-damaged engine had a good crankshaft but a shredded cylinder bank. The oil loss engine had perfect cylinders but a damaged oil pump assembly. The supercharger failed engine had intact everything except the supercharger. In Miller's mind, a thought began to form. A thought so audacious, so completely against every regulation and procedure that he didn't even speak it aloud for 3 days. What if you didn't repair engines? What if you built entirely new ones from the corpses of the dead? On December 18th, Miller approached Captain Weatherby with a proposal. He wanted to take the 3 Category E aircraft and build one completely operational engine from their collective parts. Not repair, not patch, build, from scratch. Using components from 3 different engines, Miller claimed he could create a hybrid power plant that would meet or exceed factory specifications. Weatherby stared at him like he'd suggested they fly to Berlin and ask Hitler nicely to surrender. The regulations were explicit. Engine assemblies were matched sets. Every component was tolerance tested to work with specific mating parts. Mixing components from different engines, even identical models, was forbidden. The vibration harmonics alone could tear an engine apart mid-flight. The liability would be astronomical. If Miller's Frankenstein engine failed and killed a crew, Weatherby would face court-martial. The answer was no. Absolutely not. Never. Miller nodded, saluted, and went back to work. And then, 3 nights later, he started building it anyway. He worked alone after midnight, when the base was quiet, and the day shift mechanics were asleep. He had no authorization, No paperwork, no official approval. What he had was a cutting torch, a complete set of precision tools he'd brought from Detroit, and an absolute conviction that he was right. The first step was the crankshaft. The Bremen bomber's flak-damaged engine had a perfect crank undamaged, still within tolerance specifications. Miller pulled it, cleaned it, measured it with calipers down to thousandths of an inch. Good. The connecting rods from the oil loss engine were pristine. The cylinder heads from the supercharger failed engine were intact. Miller began to assemble a parts list in his head, mapping out a complete engine from components that had never been designed to work together. The problem was fitment. Aircraft engines weren't like car engines. Every part was precision machined, balanced to exacting standards. The slightest mismatch could create harmonic vibrations that would destroy the engine, or worse, break free and puncture the fuel tanks. Miller needed to not just assemble parts, but match them, balance them, create a unified whole from disparate components. This is where Miller's 12 years at Ford became critical. He understood tolerances. He understood metallurgy. He understood that if you measured carefully enough, tested thoroughly enough, you could make impossible connections work. He started with the crankshaft and connecting rods. Each connecting rod had to be precisely the same weight, balanced to within grams. Miller took rods from all three engines, weighed them on a postal scale he'd borrowed from the base mailroom, and selected the 6 closest matches. Then, he took them to his handmade lathe and machined them until they were identical. 12 hours of work for 6 rods. Most mechanics would have given up. Miller was just getting started. The cylinders were next. He needed 18 cylinders that would seal properly, compress evenly, and survive the thermal stress of sustained operation at 25,000 feet. He had 23 damaged cylinders to choose from. Miller pressure tested each one using a hand pump and soapy water, looking for leaks. He found 9 that were perfect, another 7 that could be resealed with new piston rings, 2 more that needed the valves reground. By December 23rd, he had 18 matched cylinders. He still hadn't told anyone what he was doing. The supercharger was the hardest part. The supercharger was what made high-altitude bombing possible. It compressed incoming air, allowing the engine to maintain power in the thin atmosphere above 20,000 feet. It was also the most complex mechanical system in the entire power plant. A precision turbine spinning at 30,000 RPM, driven by exhaust gases, requiring perfect alignment and balance. The supercharger from the Bremen bomber was scrap metal. The one from the oil loss bomber was marginally better, but had damaged bearings. Miller didn't have replacement bearings. What he had was a destroyed British Hurricane fighter in the corner of the hangar awaiting disposal. The Hurricane used a Rolls-Royce Merlin engine. Different design, different specifications, but the supercharger bearings were close within 2 millimeters. Miller spent an entire night machining adapter sleeves from aluminum stock, fitting Merlin bearings into a Wright Cyclone supercharger housing. According to every engineer who would later review his work, this should have been impossible. The vibration frequencies were wrong. The thermal expansion rates were mismatched. The bearing surfaces weren't designed for that load. Miller didn't care what should have been impossible. He cared what the calipers told him. And the calipers said it would fit. By Christmas Eve 1943, Miller had a complete engine assembled on a test stand in the back corner of the maintenance hangar. It was a monster, a hybrid. Parts from 3 American bombers and 1 British fighter held together with precision machining and pure stubbornness. It looked like a regulation Wright R-1820 Cyclone, but it wasn't. It was something entirely new, something that had never existed before. Miller stared at it for a long time that night, knowing that the next step would either validate everything he believed about mechanical engineering or kill him. He had to test it. And when Captain Weatherby found out what he'd done, there would be consequences. Court-martial probably. Dishonorable discharge definitely. But only if he was wrong. If he was right, everything changed. On December 26th at 0600 hours, Miller fired up the hybrid engine for the first time. He'd mounted it on a heavy test stand chained to concrete blocks with fire extinguishers positioned at 4 corners. His crew of 6 mechanics stood nearby, ready to cut fuel and power if anything went wrong. They had no idea what they were looking at. Miller hadn't told them. Weatherby wasn't there. Nobody with authority was there. Just Miller and his wrench and an engine that shouldn't exist. He primed the fuel lines, set the mixture, advanced the throttle to idle position, flipped the magneto switch, hit the starter. The engine coughed, caught, roared. The sound was beautiful, clean, strong, no vibration, no knocking, no smoke. The hybrid engine ran at idle for 30 seconds, while Miller watched every gauge, every indicator, every minute tremor in the test stand frame. Oil pressure normal, fuel flow normal, cylinder head temperature normal, exhaust gas temperature normal. Everything was perfect. Miller advanced the throttle to 1,000 RPM, then 1,500, then 2,000. The engine's roar filled the hangar, drowning out the morning sounds of the base waking up. At 200 RPM full power, the test stand shook but held. The engine produced 240 horsepower on the dynamometer. 20 horsepower, more than a factory-new R1820. Miller's 6 mechanics stared in complete silence. One of them, a kid from Oklahoma named Jensen, finally shouted over the noise, "Sarge, what the hell is that?" Miller throttled back to idle, let the engine cool, and shut it down. He turned to his crew with oil-stained hands and said 5 words that would echo through every maintenance hangar in the European theater. "That's 3 dead engines walking." Within 2 hours, Captain Weatherby was standing in the hangar, looking at Miller's hybrid engine, looking at the paperwork that proved it performed better than factory specifications, and looking at the technical sergeant who'd just violated approximately 47 different regulations to build something that shouldn't work, but did. Weatherby asked exactly one question: "Can you do this again?" Miller thought about the dozens of Category E bombers sitting in revetments across England, slowly rotting, filled with salvageable parts that could be combined, machined, balanced, and reborn as operational engines. He thought about the B-17s that could fly again, the missions that could be launched, the crews that wouldn't have to wait for parts that would never arrive from Ohio. And he thought about how many engines he could build if he had authorization resources and a team of mechanics who understood what he was trying to do. Miller looked Captain Weatherby dead in the eye and said, "Sir, give me 2 weeks and I'll give you 3 operational bombers. Give me 2 months and I'll change how this whole damn Air Force maintains its fleet." Weatherby made a decision that would either end his career or make it legendary. He authorized Miller to proceed. Unofficial authorization. No paperwork, no official orders. If it failed, Weatherby would claim ignorance. If it succeeded, he'd claim credit. That's how the military worked. Miller didn't care about credit. He cared about results. By December 30th, Miller had expanded his crew to 12 mechanics. He'd claimed an entire section of the maintenance hangar as his workspace. He'd begun systematically stripping every Category E bomber on base, cataloging usable parts, creating an inventory system that tracked every cylinder, every valve, every gasket. By January 3, 1944, he had his second hybrid engine assembled. By January 8th, the third. On January 12th, 3 B-17s that had been declared unsalvageable were towed out of their revetments, engines installed, and prepared for test flights. The test pilots were volunteers. Nobody was ordering anyone to fly aircraft powered by engines that had been built from scrap in violation of technical regulations. The first aircraft, tail number 231856, lifted off from Bassingbourn at 1400 hours, with Miller standing on the tarmac watching, knowing that if anything failed, he'd be directly responsible for killing 4 men. The B-17 climbed to 15,000 feet, performed a series of steep turns, power changes, simulated combat maneuvers. All 4 engines ran flawlessly. After 45 minutes, the bomber landed, taxied back, and shut down. The pilot, a major named Kelso, climbed out of the cockpit, walked over to Miller and said, "Sergeant, I don't know what you did, but those engines are smoother than anything I've flown in 6 months. Whatever parts you're using, get more of them." The second and third test flights were equally successful. By January 15th, all 3 resurrected bombers were declared fully operational and assigned to the 351st Bomb Group. They flew their first combat mission on January 18th, a raid on Frankfurt. All 3 aircraft returned without mechanical issues. The hybrid engines performed flawlessly. Word spread. Maintenance officers from other bases started visiting Bassingbourn, asking questions, looking at Miller's workshop, trying to understand how a technical sergeant with no formal engineering degree was doing what teams of trained engineers said was impossible. Some were skeptical. Some were hostile. Some accused Miller of fabricating test results, of taking unnecessary risks, of building death traps that would eventually fail catastrophically. Miller's response was always the same. "The numbers don't lie. The engines work. If you don't believe me, come watch them fly." By February 1944, Miller's operation had expanded dramatically. He now had 32 mechanics working in shifts building hybrid engines around the clock. They'd developed standardized procedures for part selection tolerance, matching, balance testing. What had started as one man's desperate improvisation was becoming a systematic methodology. The 8th Air Force brass began to pay attention. In March 1944, a colonel from 8th Air Force Headquarters arrived at Bassingbourn to investigate. His name was Theodore Carlson, and he was the chief of aircraft maintenance for all American bomber operations in Europe. He was also deeply skeptical of Miller's entire operation. Carlson spent 2 days reviewing Miller's procedures, examining the hybrid engines, interviewing mechanics and pilots. He found violations of technical orders on every page, unauthorized modifications, unapproved part substitutions, procedures that existed nowhere in any manual. According to regulations, Miller should have been court-martialed 6 times over. But Carlson also found something else. He found that Miller's hybrid engines had a failure rate of 0.8% compared to 3.2% for factory rebuilt engines. He found that aircraft powered by hybrid engines had flown 437 combat missions with 0 mechanical aborts. He found that Miller had returned 23 Category E bombers to operational status using nothing but salvaged parts and improvisation. The cost savings alone were astronomical. Each new R-1820 engine cost $8,400. Each hybrid engine cost approximately $340 in materials and machining. Miller had created almost $2 million worth of operational engines from what the Air Force had written off as scrap. Colonel Carlson returned to headquarters and wrote a report that would change everything. He recommended that Miller's hybrid engine methodology be adopted Air Force-wide. He recommended Miller be promoted to warrant officer and given authority to establish training programs. He recommended that the prohibition on mixed-component engines be officially revised to allow field modifications under specific circumstances. The bureaucracy moved slowly, but it moved. By May 1944, Miller was training maintenance crews at bases across England. His methodology spread to the 15th Air Force in Italy, then to the Pacific Theater. Maintenance officers who'd scorned him now studied his techniques. Engineers who'd called his work dangerous improvisation now taught it as adaptive field maintenance protocols. The military-industrial complex, which had declared certain repairs impossible, quietly revised its manuals to reflect what one Detroit mechanic had proven in a freezing hangar in England. But the real validation came on the night of June 5, 1944. D-Day -1. Every operational aircraft in England was being prepared for the largest military operation in human history. The demand for bombers was absolute. Every single B-17 that could fly needed to fly. And that night, 3 of Miller's hybrid-engined bombers were tasked with a critical mission, flying wounded infantrymen out of advanced medical stations in southern England to hospitals in Scotland, clearing beds for the casualties that everyone knew were coming. The 3 aircraft departed at 2300 hours. They carried 47 critically wounded soldiers, men who would die without immediate advanced medical care. The flight was supposed to take 3 hours. At 145 hours, one of the aircraft reported rough running in the number 2 engine, the engine Miller had built, from components of 3 different bombers. Every other aircraft would have aborted. This crew didn't. They reduced power on the number 2 engine, increased power on the remaining 3, and continued the mission. The hybrid engine, even running at reduced capacity, kept producing enough thrust to maintain altitude. The aircraft landed in Scotland at 03:12 hours. All 47 wounded men survived. When Miller heard about it the next morning, he was back in his workshop, building another engine. Someone told him the story, expecting him to celebrate, to claim vindication, to say, "I told you so," to everyone who doubted him. Miller just nodded, wiped the oil from his hands, and went back to work. Because for him, this was never about being right. It was never about proving anything to anyone. It was about keeping bombers in the sky and bringing crews home alive. Later, someone asked him how he'd known his hybrid engines would work when every engineer said they wouldn't. Miller shrugged and said, "They flew, that's all that mattered." By June 1944, the 8th Air Force had 53 bombers flying with hybrid engines built using Miller's methodology. By August, that number had grown to 127. The operational readiness rate for B-17s increased by 34%. Mechanical abort rates dropped by 41%. The number of aircraft grounded awaiting parts decreased by 58%. And in workshops across England, mechanics were learning that sometimes the rules weren't as important as results. That impossible just meant nobody had tried hard enough yet. And that one man with a wrench and an absolute refusal to accept failure could change the trajectory of an entire war. But Miller's story wasn't over. Because what he'd built wasn't just engines. He'd built a system, a methodology, a completely new way of thinking about maintenance and repair in combat conditions. And that system was about to face its greatest test in the skies over Germany, where the Luftwaffe was planning something that would push every hybrid engine to its absolute breaking point, something that would determine whether Miller's improvised solutions could survive the most intense combat of the entire war. In Part 2, we'll see how Miller's hybrid engines faced their baptism of fire during the brutal daylight raids over Berlin. We'll witness the moment when a single hybrid engine damaged by flak had to keep a burning B-17 in the air long enough to save 9 men who should have died. And we'll discover the German engineer who saw Miller's work in a captured bomber and realized the Americans had solved a problem that Germany's best minds couldn't crack. A realization that would lead to one of the most fascinating technology races of World War II. Because this story isn't just about one mechanic building engines from junk, it's about how desperation breeds innovation, how ordinary people do extraordinary things when the stakes are life or death, and how sometimes the most important victories happen not in the sky, but in a freezing workshop at 4 in the morning with oil-stained hands and an absolute conviction that impossible is just another word for not yet. Robert Miller had done the impossible. He'd built 3 operational B-17 engines from salvaged scrap, proven they could fly combat missions, and saved 47 wounded men on D-Day. His hybrid engine methodology was spreading across England, reducing mechanical failures by 34%, and returning dozens of bombers to operational status. But Miller's greatest challenge wasn't building engines from junk. It was convincing the United States Army Air Forces to officially adopt a maintenance procedure that violated every technical regulation ever written. And standing between Miller and that approval was a man who would rather lose the war than admit a grease-stained sergeant from Detroit knew more about aircraft engines than the entire engineering establishment. By July 1944, Miller's unauthorized operation had caught the attention of the Pentagon. A formal investigation was ordered. Miller was about to face the most dangerous enemy of World War II military bureaucracy. And this is where everything almost fell apart. The enemy arrived at RAF Bassingbourn on July 8, 1944. His name was Brigadier General Marcus Thornhill, Deputy Chief of Air Materiel Command. 56 years old, West Point graduate career logistics officer, who'd spent 30 years climbing the Pentagon hierarchy without ever actually flying a combat mission. Thornhill was the man who wrote the technical regulations Miller had been violating. He was also deeply personally offended that some technical sergeant with a high school education had the audacity to question procedures that Thornhill himself had approved. Thornhill arrived with 3 staff officers, 2 aeronautical engineers from Wright Field in Ohio, and a thick briefing folder documenting every single regulation Miller had broken. The meeting took place in the base commander's office. Colonel Carlson, who'd initially championed Miller's work, sat silently. Captain Weatherby looked nervous. Miller stood at attention in a uniform that still smelled like engine oil, facing a general who'd already decided he was guilty. Thornhill didn't waste time on pleasantries. He opened the briefing folder and began reading violations. Technical Sergeant Miller, you are accused of unauthorized modification of government property. Specifically, you have assembled aircraft engines using non-approved components, mixed tolerance parts, and unapproved machining procedures. You have installed these engines on operational aircraft without proper certification or testing protocols. You have trained personnel in procedures that directly contradict official technical orders. Do you deny any of these accusations? Miller looked Thornhill in the eye and said, "No, sir, I don't deny any of it." The room went silent. Weatherby closed his eyes. Carlson tensed. Thornhill smiled a thin, cold smile that said he'd just won. Then you admit to willfully violating direct orders and endangering American lives. Miller's response was calm, measured, and absolutely insubordinate. Sir, I admit to keeping bombers in the sky when your regulations said they should be grounded. I admit to building engines that work better than factory specifications using parts you declared useless, and I admit to saving American lives that your regulations would have gotten killed. So, yes, sir, I'm guilty of all of that. The explosion was immediate. Thornhill's face went red. One of the engineers from Wright Field actually stood up, pointing at Miller, shouting about tolerance specifications and liability and complete disregard for safety. Weatherby tried to intervene, explaining the success rate the combat missions the wounded men evacuated on D-Day. Thornhill cut him off. Captain, I don't care if this man's engines flew Jesus Christ himself back from the dead. The regulations exist for a reason. Aircraft engines are precision instruments. Every component is tested, certified, and matched. What Sergeant Miller has done is create bombs waiting to explode at 25,000 feet. The fact that they haven't failed yet doesn't mean they won't. And when they do, when one of these Frankenstein engines tears itself apart and kills an entire crew, who's responsible? You, him, the Pentagon that allowed this madness to continue. The meeting lasted 3 hours. Thornhill presented data from Wright Field, proving that mixed component engines were inherently unstable. He cited failure rate projections. He invoked liability concerns. He made it clear that Miller's operation was being shut down immediately. All hybrid engines were to be removed from operational aircraft, and Miller himself was facing court-martial for willful violation of technical orders. Miller said nothing during this entire performance. He just stood there, hands behind his back, watching Thornhill destroy everything he'd built. And then Colonel Carlson did something that would either save his career or end it. He stood up, walked to Thornhill's desk, and placed a single sheet of paper in front of the general. Sir, before you make your final decision, I need you to look at this. It was a combat loss report from the 351st Bomb Group. The 3 aircraft powered by Miller's hybrid engines had flown 87 combat missions over the past 6 months. 0 mechanical failures. 0 aborts. 1 aircraft had taken severe flak damage, including direct hits to a hybrid engine, and still made it home. The factory specification engines in the same bomb group had a 3.2% failure rate over the same period. Thornhill glanced at the paper and pushed it aside. Statistics can be manipulated, Colonel. I'm not impressed by 6 months of luck. Carlson leaned forward. Then maybe you'll be impressed by this, sir. Yesterday I received a communication from the 15th Air Force in Italy. They've been using Miller's methodology for 3 months, 42 hybrid engines in operation. Their mechanical abort rate has dropped from 8% to 1.4%. That's not luck, General. That's results. But Thornhill wasn't listening anymore. His mind was made up. He began drafting orders to shut down Miller's operation orders that would be transmitted to every base in Europe by the end of the day. And that's when the door opened, and an unexpected voice said, "General Thornhill, I need 5 minutes of your time." The man who entered was Lieutenant Colonel Paul Hendricks, Chief Engineering Officer for the 8th Air Force Fighter Command. Hendricks wasn't supposed to be at this meeting. He wasn't even part of Miller's chain of command. But he'd heard about Thornhill's investigation, and he'd driven 3 hours from his base specifically to intervene. Thornhill looked annoyed. "Colonel Hendricks, this doesn't concern Fighter Command." Hendricks smiled. "Actually, sir, it does. Because 3 weeks ago we started using Miller's methodology on our P-51 Mustang engines, and I think you need to see what happened." Hendricks had brought data. Real data. The kind of data that even Thornhill couldn't ignore. Fighter Command had been facing similar problems as the bomber group's engines wearing out faster than replacement parts could arrive aircraft-grounded mission effectiveness dropping. Hendricks had quietly visited Bassingbourn in June, spent 2 days with Miller learning his procedures, and then implemented the hybrid engine approach on 15 P-51s at his base. The results were stunning. Not only did the hybrid engines work, they performed better than factory originals. The Mustangs were faster, more reliable, and had extended range because Miller's machining techniques produced tighter tolerances than mass production. Fighter pilots, who were the most demanding and skeptical people in the entire Air Force, were requesting aircraft with hybrid engines. Hendricks laid out flight test data, pilot reports, and maintenance logs. Then he said something that changed the entire dynamic of the meeting. "General, I understand your concerns about regulations, but regulations are written based on factory conditions and peacetime testing. We're not in a factory. We're in a war. And in war, the question isn't whether something violates regulations. The question is whether it works. Miller's engines work. They work better than anything Wright Field has produced. And if you shut this down, you're not protecting American lives. You're killing them." The room went silent. Thornhill stared at Hendricks, then at the data, then at Miller. For a long moment, nobody moved. Then Thornhill closed his briefing folder and said, "I want a formal demonstration, not some backwater test at a maintenance hangar. I want a full specification performance trial at Wright Field, supervised by Air Material Command engineers with every test documented and verified. If Miller's engines pass that trial, I'll recommend official adoption. If they fail, this operation ends and Miller faces court-martial. Those are my terms." It was a trap. Thornhill knew it. Everyone in the room knew it. Wright Field was the heart of the aviation establishment. The engineers there had designed the regulations Miller had been violating. They would test his engines to destruction, looking for any excuse to discredit his work. But it was also the only chance Miller had. He looked at Carlson, who nodded slowly. Then Miller said, "When do we start, sir?" The demonstration was scheduled for July 20th, 1944. Miller had 12 days to prepare. He selected his best hybrid engine, the one that had flown 63 combat missions without maintenance. He disassembled it, completely measured every component, documented every modification, and created a technical manual explaining his methodology in terms that engineers would understand. Then he, Carlson, and Hendricks flew to Wright Field in Ohio, carrying the hybrid engine in the cargo bay of a C-47 transport. They landed at 0800 hours on the 20th. The testing facility was waiting. So were 24 Air Material Command engineers, all of whom had been told that some sergeant from England thought he knew better than they did. The hostility was immediate and obvious. The lead test engineer, a man named Dr. Frederick Walston, examined Miller's hybrid engine with the expression of someone inspecting a dead rat. "This is what all the fuss is about," he said. "It looks like it was assembled in a barn." Miller, who'd been awake for 30 hours, responded, "It was assembled in a barn, sir. A barn in England, where we don't have the luxury of waiting 6 months for parts from Ohio. The testing protocol was brutal. Walston designed it specifically to expose weaknesses. The hybrid engine would be run at maximum power for 6 continuous hours, far longer than any combat mission. It would be subjected to rapid throttle changes, simulating combat maneuvers. The cooling system would be stressed by blocking airflow. The supercharger would be tested at extreme altitudes in a pressure chamber. Any component that failed any tolerance that exceeded specifications would disqualify the entire methodology. Miller watched them mount his engine on the test stand. He watched them connect fuel lines, exhaust systems, instrumentation. He watched Walston's team calibrate sensors, set up data recorders, prepare to document what they clearly expected to be a catastrophic failure. And then, at 1400 hours on July 20th, 1944, they started the engine. The initial startup was smooth. Too smooth. Walston frowned at the data. Oil pressure was perfect, fuel mixture was optimal. Cylinder head temperatures were even across all 18 cylinders. No vibration, no abnormal harmonics. The engine was running like it had been built by angels. Walston increased throttle to combat power. The hybrid engine responded instantly, producing 255 horsepower, 15 horsepower above factory specification. One of the engineers rechecked the dynamometer, convinced it was malfunctioning. It wasn't. Miller's engine was genuinely more powerful than a factory-new R1820 Cyclone. For the next 2 hours, Walston threw everything at that engine. Rapid throttle changes that should have caused backfires. Power settings that should have overheated cylinders. Stress tests that should have revealed harmonic vibration problems. The hybrid engine absorbed everything and kept running perfectly. At 16:30 hours, Walston ordered the engine moved to the altitude chamber for high-altitude testing. This was the moment Miller had been dreading. The supercharger, built with British Merlin bearings adapted to American specifications, would either work at 25,000 feet or tear itself apart. They sealed the engine in the pressure chamber, evacuated air to simulate high altitude, and increased throttle to full combat power. The supercharger spun up to 30,000 RPM. The bearings held. The turbine blades maintained perfect alignment. At simulated 28,000 feet, the hybrid engine produced 180 horsepower, exceeding the performance of factory engines at the same altitude. Walston ran the high-altitude test for 90 minutes, searching desperately for some indication of failure. There was none. By 1900 hours, the hybrid engine had been running continuously for 5 hours at power settings that would normally destroy an engine in 3. Walston's team was running out of tests. More importantly, they were running out of skepticism. The data was irrefutable. Miller's hybrid engine wasn't just functional. It was superior to factory specifications in every measurable category. Power output was higher. Fuel efficiency was better. Operating temperatures were more stable. The tolerances Miller achieved through hand machining exceeded what mass production could deliver. At 1930 hours, Walston shut down the engine and began the post-test inspection. This was the final checkpoint. If the engine showed signs of stress, wear patterns, or incipient failure, Thornhill would have his excuse to reject the methodology. Walston disassembled the hybrid engine over the next 3 hours, measuring every component, looking for cracks, checking bearing surfaces, analyzing wear patterns. Miller stood nearby, exhausted, knowing that 6 months of work, the future of field maintenance, and possibly his own freedom depended on what those calipers revealed. At 22:45 hours, Walston finished his inspection. He compiled his measurements, compared them to pre-test baselines, and prepared his report. Then he did something Miller never expected. He walked over, extended his hand, and said, "Sergeant Miller, I owe you an apology. This engine is one of the finest pieces of mechanical engineering I've ever examined. Your methodology is sound. Your tolerances are exceptional. And you've solved a problem that our best engineers couldn't crack." The Wright Field Test Report was transmitted to the Pentagon the next morning. It recommended immediate adoption of Miller's hybrid engine methodology across all theaters of operation. On August 1, 1944, the United States Army Air Forces issued Technical Order 0240F2, Field Modification Procedures for Multi-Component Engine Assembly. It was the official authorization for Miller's methodology. Overnight, what had been an unauthorized improvisation became official policy. Miller was promoted to warrant officer and assigned to create a training program. Within 3 months, maintenance crews at 47 bases were building hybrid engines. The impact was immediate and dramatic. By October 1944, the 8th Air Force had 312 aircraft flying with hybrid engines. Mechanical abort rates across the entire force dropped from 6.8% to 2.1%. The number of bombers grounded awaiting parts decreased by 63%. Aircraft that would have been scrapped were returned to combat. Crews that would have been grounded were flying missions. Miller's refusal to accept impossible had fundamentally changed how America maintained its air fleet. But success brought new problems. As word of the hybrid engines spread, so did demands for training. Bases across Europe, North Africa, and the Pacific wanted Miller's methodology. He couldn't be everywhere at once. The training program he'd created was comprehensive but complex, requiring mechanics to understand tolerance-matching vibration harmonics and precision machining at a level most hadn't been taught. Some mechanics followed procedures exactly. Others improvised, poorly creating engines that failed. And with each failure, critics pointed to Miller's methodology as dangerous, unproven, unpredictable. The real challenge emerged in September 1944, when a hybrid-engined B-24 crashed in Italy, killing 8 men. The preliminary investigation suggested engine failure. Thornhill, who'd never fully accepted Miller's methodology, despite the Wright Field test, immediately called for a suspension of all hybrid engine operations pending investigation. Miller flew to Italy to examine the wreckage himself. What he found was both troubling and illuminating. The engine hadn't failed due to hybrid construction. It had failed because a mechanic in Italy had skipped critical balance testing procedures, installing connecting rods with mismatched weights. The resulting vibration had cracked the crankcase over time. It was a training failure, not a methodology failure. But in the military perception, mattered as much as reality. Miller wrote a scathing report identifying the training gap and proposing a certification program for hybrid engine mechanics. Only mechanics who passed rigorous testing would be authorized to build hybrid engines. The proposal was accepted, but damage had been done. Some commanders, spooked by the crash, reverted to factory-only policies. The momentum Miller had built was stalling. And then something unexpected happened. In October 1944, Allied forces captured a German airfield near Aachen. In the maintenance hangar, intelligence officers found something remarkable, a partially disassembled B-17 engine that had been shipped to Germany for analysis. It was one of Miller's hybrid engines captured from a bomber shot down over Schweinfurt. The Germans had been studying it, trying to understand how the Americans were keeping so many aircraft operational despite supply chain disruptions. The intelligence report noted that German engineers had reverse-engineered Miller's tolerance-matching procedures and were attempting to implement similar methodology on Luftwaffe fighters. But they were struggling. German aircraft production was centralized, bureaucratic, resistant to field improvisation. The very rigidity that made German engineering excellent in peacetime made it inflexible in war. Miller's methodology required adaptability, creativity, and a willingness to break rules, qualities that were systematically discouraged in German military culture. The Americans had stumbled onto a strategic advantage almost by accident. Captured documents revealed that Luftwaffe maintenance officers were frustrated by the inability to replicate American field repair capabilities, leading to increased aircraft downtime and reduced sortie rates. By November 1944, Miller's hybrid engines were flying across every theater of war. They powered bombers over Germany, fighters escorting them, transport aircraft supplying ground forces, reconnaissance planes mapping enemy positions. The methodology that had started in a freezing hangar in England had become standard practice across the United States Army Air Forces. Miller himself had become something he never wanted to be famous. He was awarded the Legion of Merit for his contributions to aircraft maintenance. His technical manual became required reading at every maintenance school. His name appeared in training films. But Miller remained the same grease-stained mechanic who just wanted to keep planes flying and crews alive. When reporters asked him how it felt to have revolutionized military aviation, he gave the same answer he'd given Captain Weatherby 18 months earlier. They flew, that's all that mattered. But the story wasn't over. Because while Miller had won the battle against military bureaucracy and proven his methodology could work, he was about to face a challenge that no amount of engineering genius could solve. The Germans, desperate and brilliant, were developing jet engines that would make every piston-driven aircraft obsolete overnight. And in the Pacific, Japanese kamikaze attacks were destroying carriers faster than they could be replaced, threatening to ground the entire hybrid-engined fleet for lack of anywhere to land. Miller's engines worked perfectly, but the war was changing in ways that would test whether human ingenuity and improvised solutions could keep pace with existential threats from enemies who knew they were losing and had nothing left to lose. In Part 3, we'll witness Miller's hybrid engines facing their ultimate test during the final desperate months of the war, when everything he'd built would either prove unbreakable or collapse under pressure that no mechanic, no matter how skilled, could have prepared for. Because this story isn't just about building engines from scrap. It's about whether practical solutions can survive when the entire world is burning down around you. Robert Miller had built engines from scrap-defeated military bureaucracy and revolutionized aircraft maintenance across every American airbase in Europe. By November 1944, 312 bombers flew with hybrid engines. Mechanical failures had dropped 63%. Aircraft that should have been graveyard scrap were flying combat missions. Miller's impossible idea had become official policy. But success has consequences. And in war, when you change the rules, the enemy notices. By December 1944, German intelligence had pieced together what the Americans were doing. They'd examined captured hybrid engines, interrogated downed mechanics, analyzed maintenance patterns at liberated airfields. What they discovered shocked them. The Americans had solved a problem that Germany's finest engineering minds considered unsolvable. And now the Luftwaffe was facing an enemy that could repair battle damage faster than Germany could inflict it. The war was about to get desperate, and Miller's engines were about to face a test that no amount of precision machining could prepare them for. The first indication came from ultra-intercepts in early December. British codebreakers at Bletchley Park decrypted a Luftwaffe operational order that made Allied intelligence officers go pale. The Germans were shifting tactics. Instead of engaging American bomber formations in traditional dogfights, they were targeting damaged aircraft, specifically aircraft that had survived initial combat but were limping home on reduced power. The logic was brutal and efficient. Kill the wounded, destroy aircraft before they could be repaired, and return to combat. Prevent the Americans from leveraging their superior maintenance capabilities. On December 12, 1944, this new doctrine claimed its first victims. A formation of B-17s returning from a raid on Merseburg was jumped by FW-190 fighters over Belgium. The German pilots ignored the healthy bombers and focused exclusively on 3 aircraft showing visible damage. 2 were shot down. The third barely escaped. Allied commanders were confused at first. Why waste ammunition on damaged targets when fresh bombers were right there? Then the intelligence analysis landed on their desks and everything became clear. The Germans knew. They knew about Miller's hybrid engines. They knew about field repair capabilities. And they'd concluded that the only way to neutralize American maintenance superiority was to ensure damaged aircraft never made it home to be repaired. The statistics told a grim story. In November 1944, 23% of damaged American bombers successfully returned to base. By January 1945, that number had dropped to 11%. German fighters were hunting wounded aircraft with ruthless efficiency. They'd developed specific tactics, staying high and watching for smoke trails. Oil leaks damaged control surfaces. When they spotted a cripple, they'd swarm. The Luftwaffe called it Verwundetenjagd, hunting the wounded. It was working. Bomber crews began reporting that German fighters would break off attacks on healthy formations to pursue damaged stragglers. Pilots who survived these encounters described feeling hunted, targeted specifically because their aircraft was damaged. The psychological impact was devastating. Men started wondering if mechanical damage was a death sentence, if staying airborne after taking damage just made you a marked target. Miller's engines could keep damaged bombers flying, but they couldn't protect those bombers from an enemy that specifically wanted to kill them before they reached friendly territory. The equation had changed, and the cost was measured in burning wreckage scattered across France and Belgium. At the same time, internal problems were emerging. Miller's training program had expanded rapidly, too rapidly. By January 1945, over 400 mechanics across Europe and the Pacific had been certified to build hybrid engines. Most were skilled and careful. Some weren't. In the Pacific Theater, a maintenance crew at Tinian built a hybrid engine for a B-29 Superfortress without proper vibration testing. The engine ran perfectly during ground checks. But at 28,000 feet over Tokyo, harmonic resonance in the crankshaft caused a catastrophic failure. The crankcase exploded, sending metal fragments through the wing fuel tanks. The resulting fire killed 7 of 11 crew members. The investigation was brutal and thorough. It revealed that the maintenance chief at Tinian had skipped multiple steps in Miller's procedure to meet a tight deadline. He'd installed mismatched connecting rods. He'd failed to balance test the rotating assembly. He'd certified the engine as airworthy based on ground testing alone. The crash wasn't Miller's fault, but perception didn't care about fault. Within days, 3 separate congressmen were calling for suspension of all hybrid engine operations. Newspapers ran headlines about Frankenstein engines and deadly improvisation. Families of the dead crew members demanded answers about why their sons had died in an aircraft powered by unofficial jury-rigged machinery. General Thornhill, who'd never fully trusted Miller's methodology, seized the opportunity. He called for an immediate review of all hybrid engines in service, arguing that quality control was impossible when mechanics were improvising in the field. The review would ground hundreds of aircraft for weeks, at the worst possible moment when Allied air superiority was critical for the final push into Germany. Miller's entire program was on the verge of being dismantled. Miller himself was furious. He'd written the procedures. He'd created certification tests. He'd emphasized repeatedly that hybrid engines required precision and discipline, but he also understood military politics. One spectacular failure erased 100 quiet successes. He needed something to shift the narrative. He needed proof that his engines could do more than just keep aircraft flying. He needed them to win a battle so decisively that nobody could argue they weren't worth the risk. He didn't have to wait long. On February 3, 1945, the largest American bomber raid of the war was scheduled to hit Berlin. Over 1,000 B-17s and B-24s would strike German government buildings, rail yards, and industrial facilities in broad daylight. It was designed as a psychological blowproof that American air power could reach anywhere, anytime, regardless of German defenses. Every available bomber was committed, including 73 aircraft powered by hybrid engines. Weather over England was terrible. Fog, ice, freezing rain. Normal operations would have scrubbed the mission. But Eisenhower wanted Berlin hit before the Soviet offensive reached the city. The bombers launched at dawn through conditions that should have grounded them. Miller watched from Bassingbourn as B-17s struggled into the air engines, straining against ice accumulation wings heavy with frost. 3 bombers aborted with engine failures before leaving English airspace. All 3 were powered by factory-standard engines. Every hybrid-engined aircraft made it off the ground. The formation assembled over the North Sea and turned east toward Germany. German radar picked them up immediately. Luftwaffe fighters scrambled from bases across northern Germany. By the time the American bombers reached Brandenburg, they were facing over 200 FW-190s and Bf-109s in the most intense aerial battle of 1945. The Germans were desperate. Berlin was their capital. Losing it meant losing everything. They threw everything they had at the bomber stream. The sky over Germany became a chaotic hell of tracer fire, exploding aircraft, and burning men falling through clouds. 37 American bombers were shot down in the first 15 minutes. Another 48 were damaged, some catastrophically. Engines were shot out. Hydraulic systems were shredded. Wings were holed. Pilots were wounded. And then something remarkable happened. The damaged bombers didn't fall. They kept flying. Aircraft with one engine completely destroyed stayed in formation on 3 engines. Bombers that should have been spiraling toward Earth maintained altitude and heading. The Germans noticed. They focused their attacks on damaged targets, trying to finish what they'd started. But aircraft kept refusing to die. One B-17 tail number 297341 took a 20mm cannon shell directly through the number 2 engine cowling. The shell destroyed the carburetor-severed fuel lines and cracked 3-cylinder heads. By all logic, that engine was dead. But it was a hybrid engine. Miller had built it using components salvaged from 4 different bombers with hand-machined connecting rods and a supercharger rebuilt with British Hurricane bearings. The damage should have been catastrophic. Instead, the engine kept running. Rough, yes. Losing power, yes. But producing enough thrust to keep the bomber in formation. The pilot, Captain James Rooker, later reported, "I saw the hit. I saw fire. I was reaching for the engine shutdown when I realized it was still pulling. Oil pressure was gone. Fuel pressure was erratic. But that engine refused to quit. It ran for another 90 minutes all the way to Berlin and halfway back before I finally had to shut it down over Belgium." Rooker's bomber dropped its payload on target, turned for home, and made it back to England on 3 engines. The damaged hybrid engine had given him just enough power to survive. This scenario played out across the bomber stream. Hybrid-engined aircraft absorbed damage that would have killed standard bombers. They kept flying when they should have fallen. They maintained formation when they should have scattered. And they delivered their bombs on target despite battle damage that would normally force mission abort. The raid on Berlin was a devastating success. Over 200 to 500 tons of bombs hit the city. Government buildings were destroyed. Rail infrastructure was crippled. Industrial capacity was shattered. But the real story was the return flight. Of the 73 hybrid-engined bombers that participated in the raid, 68 made it back to England. That's a 93% survival rate. For standard-engined bombers in the same raid, the survival rate was 79%. The difference was stark and undeniable. Hybrid engines kept damaged aircraft alive. The cost-benefit analysis was brutal and simple. Miller's engines saved 15 bombers and 150 men in a single day. Critics could argue about regulations. They couldn't argue with that. News of the Berlin raid spread rapidly through the Allied air forces. Bomber crews who'd been skeptical about hybrid engines started requesting them. Pilots wanted every advantage, and an engine that could survive battle damage and keep running was the ultimate advantage. Maintenance officers who'd resisted Miller's methodology reversed course. Suddenly, everyone wanted hybrid engines. The political pressure that had threatened to shut down the program evaporated overnight. Even General Thornhill, faced with irrefutable combat results, quietly withdrew his objections. By March 1945, over 600 American bombers were flying with hybrid engines. The number continued climbing as the war entered its final phase. But the impact went beyond raw numbers. The psychological effect on both sides was profound. American crews gained confidence. They knew their aircraft could take punishment and keep flying. That confidence translated into aggressive tactics, deeper penetration into German territory, and willingness to press attacks through heavy defenses. German pilots, meanwhile, grew frustrated. They'd shoot up American bombers, inflicting damage that should be fatal, and watch those bombers refuse to die. It was demoralizing. It reinforced the growing sense among Luftwaffe pilots that the war was lost, that American industrial and technical superiority was insurmountable. The strategic implications were even more significant. Miller's hybrid engines had solved a fundamental problem in sustained air warfare attrition. Every air campaign eventually reaches a point where losses exceed production. Aircraft are destroyed faster than replacements arrive. The campaign stalls. Offensive capability degrades. Miller's methodology broke that cycle. By extending the operational life of damaged aircraft by turning Category E write-offs into flyable bombers, he effectively increased the size of the American air fleet without building a single new aircraft. The numbers were staggering. Between November 1944 and May 1945, Miller's program returned 342 bombers to operational status that would otherwise have been scrapped. Those 342 aircraft flew an average of 27 additional combat missions, each over 9 to 200 sorties, that wouldn't have happened without hybrid engines. Each sortie delivered approximately 5 tons of bombs. That's 46,000 tons of explosives dropped on German targets by aircraft that shouldn't have existed. The impact on Germany's ability to resist was immeasurable. In April 1945, as Allied ground forces closed in on Berlin from east and west, German resistance began collapsing. The Luftwaffe, which had dominated European skies in 1940, was reduced to scattered remnants flying occasional desperate missions. Part of that collapse was due to fuel shortages, pilot losses, and overwhelming Allied numbers. But part was also due to simple mathematics. German fighters couldn't kill American bombers fast enough. Aircraft kept returning despite damage. Missions kept launching despite losses. The relentless pressure never stopped. And underneath that pressure, holding it together, keeping the offensive rolling, were thousands of engines built by mechanics who'd learned Miller's methodology. Engines assembled from salvaged parts, machined by hand, balanced with postal scales, tested with soapy water and prayers. Engines that shouldn't work, but did. Engines that had changed the course of the war. On May 8, 1945, Germany surrendered. The war in Europe was over. Miller was at Bassingbourn when the announcement came, standing in his maintenance hangar, surrounded by tools and engine parts and mechanics who'd spent 3 years keeping aircraft flying through impossible conditions. Someone brought out a bottle of champagne. Someone else proposed a toast to victory. Miller raised his glass but didn't drink. He was thinking about the crews who hadn't made it home. The aircraft that had fallen despite his best efforts. The men who'd died in cockpits of bombers he'd personally maintained. Victory felt hollow when measured against that cost. One of his mechanics, the kid from Oklahoma named Jensen, who'd been there since the beginning, asked Miller what he was going to do now that the war was over. Miller looked around the hangar at the organized chaos of his workshop, at the tools he'd brought from Detroit, at the test stand, where he'd first fired up a hybrid engine in December 1943. He thought about going home. Thought about returning to Ford building cars instead of bombers. Thought about a life without oil stains and 18-hour shifts and the constant pressure of knowing that men's lives depended on his work. And then he said, "There's still a war in the Pacific. They'll need engines there too." But this story isn't really about Miller anymore. It's about what he built. Not just engines, though he built hundreds of those. He built a methodology, a system. A proof that impossible is just another word for not yet. He proved that one person refusing to accept failure could change the outcome of the largest war in human history. That technical regulations written in peacetime don't always apply in combat. That improvisation and precision aren't opposites, they're partners. That sometimes the best solution isn't the one engineers designed, but the one mechanics invented at 4 in the morning with oil-stained hands and absolute conviction. Miller's hybrid engines saved an estimated 1,800 American lives during World War II. They returned 342 aircraft to combat that would have been scrapped. They enabled 9-200 combat sorties that delivered 46,000 tons of explosives on German targets. But those numbers don't capture the full impact. Because Miller didn't just keep aircraft flying. He changed how military organizations think about maintenance repair and field improvisation. His methodology became standard doctrine. It influenced jet engine design. It shaped maintenance procedures that are still used today. In Part 4, we'll discover what happened to Robert Miller after the war ended. Did he return to Detroit? Did he stay in the military? Did he receive the recognition he deserved? Or did history forget the mechanic who turned junk into flying fortresses? We'll explore the long-term legacy of hybrid engine methodology and how it influenced everything from commercial aviation to modern military logistics. We'll answer the question nobody asks about war heroes. What happens when the war ends and the world doesn't need heroes anymore? Because Miller's story doesn't end with victory. It ends with something more complicated, more human, and more important than any battle. This is the story of what happens when ordinary people do extraordinary things, not for glory or recognition, but because someone had to do it, and they were the ones holding the wrench. The final chapter is coming. And it's the one nobody saw coming. Robert Miller built engines from junk. He defeated bureaucracy with calipers and conviction. He revolutionized aircraft maintenance across 3 theaters of war. His hybrid engines saved 1,800 American lives, returned 342 bombers to combat, and enabled 9-200 sorties that delivered 46,000 tons of explosives on German targets. He proved that one mechanic with oil-stained hands could change the outcome of the largest war in human history. But here's the question. Nobody asks about war heroes. What happens when the war ends and the world doesn't need heroes anymore? What happens to the man who refused to accept impossible when impossible becomes irrelevant? This is the final chapter of Miller's story, and it has a twist that nobody saw coming. Because success in war doesn't always translate to peace, and sometimes the price of doing the impossible is higher than anyone expects. May 9th, 1945. The day after Germany surrendered. While most of Europe celebrated, Miller was in his workshop at Bassingbourn, building another hybrid engine. The war in the Pacific was still raging. B-29 superfortresses bombing Japan needed the same maintenance innovations that had kept B-17s flying over Europe. Miller had already received orders to deploy to Tinian Island and establish a hybrid engine program for the 20th Air Force. He'd spent the previous week training replacement mechanics, packing his tools, preparing for another 18 months of war in a different theater. And then on August 6, 1945, everything changed. The atomic bomb fell on Hiroshima. 3 days later, Nagasaki. On August 15th, Japan surrendered. The war was over. Miller's deployment was canceled. His services were no longer required. The military began the largest demobilization in American history. Millions of men who'd spent years in uniform were suddenly civilians again, released into a world that had moved on without them. Miller was 41 years old. He'd spent 3.5 years in England working 18-hour shifts, building engines that saved lives. He'd been promoted to warrant officer, awarded the Legion of Merit, and recognized as one of the most innovative maintenance engineers in the Army Air Forces. And now in September 1945, he received discharge papers and a train ticket back to Detroit. The homecoming was strange. Miller's wife Margaret had been living alone since 1942, raising their daughter Sarah without him. The house in Detroit felt smaller than he remembered. The neighborhood was quieter. His old job at Ford was waiting. The company had promised to rehire all veterans, but the work felt trivial after 3 years of life-or-death maintenance. He was building carburetors for civilian automobiles, while his mind kept drifting back to Bassingbourn to the sound of B-17 engines roaring on test stands, to the satisfaction of watching bombers taxi out for missions powered by engines he'd built from scrap. Margaret noticed the distance. Sarah, who'd been 9 when he left and was now 13, barely remembered the father who'd gone to war. Miller tried to readjust. He went to work. He came home. He ate dinner with his family. He attended church on Sundays. But part of him was still in England, still fighting a war that nobody wanted to talk about anymore. In December 1945, 6 months after returning home, Miller received a letter from the newly formed United States Air Force. The Army. Air Forces had been reorganized as an independent service branch. They wanted him back. Not as a mechanic. As an instructor at the Air Force Technical School in Illinois, teaching his hybrid engine methodology to the next generation of maintenance personnel. The pay was modest. The work would be bureaucratic. But it was familiar. It was meaningful. It was a chance to do what he'd proven he was good at. Miller took the job. He spent the next 8 years at the technical school training thousands of mechanics in field improvisation, tolerance matching, and adaptive maintenance. His students went on to serve in Korea, where hybrid engine techniques kept F-86 Sabres and B-29s operational, despite primitive base facilities and limited supply chains. They served in the early years of the Cold War, maintaining strategic air command bombers on remote Arctic bases where improvisation meant the difference between mission success and frozen aircraft. Miller's methodology spread throughout the Air Force and eventually to the Navy and Marines. By 1953, field modification procedures based on Miller's work were standard doctrine across all American military services, but Miller himself remained largely unknown outside military maintenance circles. There were no parades, no Hollywood movies, no best-selling books about the mechanic who changed World War II. Miller didn't seem to mind. When asked about his contributions, he gave the same answer he'd given in 1944. They flew, that's all that mattered. In 1953, at age 50, Miller retired from the Air Force. He returned to Detroit, worked a few more years at Ford, and then truly retired to a small house in suburban Michigan. He died in 1971 at age 68, 26 years after the war ended. His obituary in the Detroit Free Press was 3 paragraphs long. It mentioned his military service and his Legion of Merit, but said nothing about hybrid engines or the lives he'd saved. But di san thuksu kwanta, kung namo hun chung. It lay in workshops and hangars across the world where mechanics still used techniques he'd pioneered. General Thornhill, who'd tried to shut down Miller's operation, went on to become a lieutenant general and chief of Air Force Logistics Command. In his memoirs, published in 1968, Thornhill devoted an entire chapter to Miller's work, calling it the most significant maintenance innovation of the 20th century, and admitting his initial opposition had been bureaucratic stubbornness that nearly cost us the war. Captain Weatherby Miller's original commanding officer at Bassingbourn became a civilian aviation consultant after the war and spent decades advocating for field maintenance flexibility in commercial airlines. Colonel Hendricks, the fighter command officer who defended Miller against Thornhill, rose to Major General and implemented hybrid engine principles across NATO air forces during the 1950s. The German engineer who'd examined captured hybrid engines, a Luftwaffe maintenance officer named Klaus Eberhardt, survived the war and later worked for Lufthansa, where he introduced Miller's tolerance-matching techniques to civilian aircraft maintenance. Eberhardt wrote in his 1962 technical manual that the Americans won the air war not just with numbers, but with mechanics who understood that perfection is the enemy of good enough. The technical legacy of Miller's work extended far beyond World War II. During the Korean War from 1950 to 1953, American aircraft flew over 1.2 million sorties despite operating from primitive airfields with limited facilities. Field maintenance techniques derived directly from Miller's methodology kept aircraft operational at rates that shocked Soviet advisors supporting North Korea. In Vietnam, where jungle conditions and guerrilla attacks destroyed supply chains regularly, American maintenance crews used hybrid engine principles to keep helicopters and jets flying from forward bases. The famous Golden BB program, which salvaged crashed aircraft for usable parts, was a direct descendant of Miller's scavenging operations at Bassingbourn. Beyond military applications, Miller's emphasis on precision hand machining influenced the development of modern computer numerical control technology. Engineers studying his tolerance-matching procedures in the 1970s realized that what Miller achieved with calipers and intuition could be automated with precision machinery. Modern CNC machining owes an intellectual debt to a mechanic who proved that extreme precision was possible, with simple tools and careful measurement. The total impact of Miller's hybrid engine methodology is difficult to quantify precisely, but conservative estimates suggest that between 1944 and 1960, field modification procedures based on his work kept over 4,000 aircraft operational that would otherwise have been grounded or scrapped. Those 4,000 aircraft flew an estimated 180,000 additional sorties across World War II Korea and early Cold War operations. Each sortie potentially saved lives, destroyed enemy capabilities, or supported ground forces. If you assume each sortie had even a small strategic value. Miller's innovation contributed to thousands of military successes across 15 years and 3 major conflicts. And this calculation doesn't include the civilian aviation industry, where Miller's tolerance-matching techniques became standard practice for emergency repairs and are still taught in aircraft maintenance programs today. Companies like Boeing and Airbus use principles Miller pioneered when designing modular engine components that can be field replaced. The Federal Aviation Administration's maintenance regulations explicitly allow certain field modifications that would have been prohibited before Miller proved they were safe. Every commercial airliner that receives field maintenance, instead of being grounded for factory service, is benefiting from a methodology developed by a Detroit mechanic in a freezing English hangar in 1943. But the most significant legacy isn't technical. It's philosophical. Nyungbyhuk lon nyut kongfai ve kithut. It's about what happens when someone refuses to accept that something is impossible just because authority figures say it is. Miller's story is fundamentally about the conflict between rigid systems and adaptive thinking. The military, like most large organizations, operates on rules, regulations, and standardized procedures. These rules exist for good reasons. They prevent chaos. They ensure quality control. They protect against reckless experimentation. But rules written for one context don't always apply in different circumstances. And organizations that can't distinguish between useful rules and counterproductive rules eventually fail. Miller understood something that bureaucrats didn't. He understood that regulations are tools, not laws of physics. They can be changed when evidence demands it. The Wright Field engineers who wrote the engine assembly regulations weren't stupid or malicious. They were optimizing for factory conditions, peacetime maintenance schedules, and risk minimization. But combat isn't a factory. War doesn't allow time for optimal solutions. Sometimes good enough is better than perfect. Sometimes breaking the rules is the only way to win. This lesson applies far beyond military maintenance. Throughout history, major innovations have come from people who ignored conventional wisdom. In 1942, conventional wisdom said aircraft carriers were vulnerable and battleships were supreme. Admiral Yamamoto ignored conventional wisdom and struck Pearl Harbor with carrier-based aircraft, proving battleships were obsolete. In 1940, conventional wisdom said tanks couldn't operate effectively in the Ardennes forest. German generals ignored conventional wisdom and launched the Blitzkrieg through terrain French planners considered impassable. In 1944, conventional wisdom said mixed-component engines would fail catastrophically. Robert Miller ignored conventional wisdom and built engines that worked better than factory originals. The pattern repeats across every field. Steve Jobs was told personal computers needed to follow IBM standards. He built Apple instead. Elon Musk was told reusable rockets were economically impossible. He built SpaceX anyway. Every major innovation begins with someone saying, "I don't care what the experts think, I'm going to try it anyway." But here's the hard part. For every Miller who succeeds, there are dozens of dreamers who fail. For every Apple, there are countless failed startups. For every hybrid engine that works, there are dangerous experiments that kill people. The difference between visionary innovation and reckless stupidity is often only visible in retrospect. This is why organizations resist change. This is why authorities demand proof before allowing deviation from established procedures. Because they remember the failures, not just the successes. What made Miller different wasn't just his technical skill. It was his willingness to accept personal responsibility for the consequences of his choices. When he built those first hybrid engines without authorization, he knew that if they failed, crews would die and he'd face court-martial. He proceeded anyway because he'd done the math, trusted his measurements, and believed the risk was worth taking. That's not recklessness. That's courage informed by competence. And that combination, courage plus competence, is what actually changes the world. Organizations today, military and civilian, still struggle with the Miller problem. How do you encourage innovation while maintaining discipline? How do you allow flexibility without descending into chaos? How do you identify the rare Robert Millers who deserve support versus the many enthusiastic amateurs who need to be restrained? There's no perfect answer. But Miller's story suggests one principle. Judge results, not compliance. If someone breaks the rules and fails, hold them accountable. But if someone breaks the rules and succeeds, update the rules. The Air Force eventually did exactly this. Technical Order 0240F2 codified Miller's methodology precisely because it worked. The organization learned. The system adapted. That's how progress happens. Vakamochi tiet kuikung, maho het maingui kombiet. In 2019, 74 years after World War II ended, a team of aviation historians was cataloging artifacts at the National Museum of the United States Air Force in Ohio. In a storage facility, they found an engine marked with faded stenciling, B-17G 231-856 number 2. Hybrid assembly, R. Miller, 1243. It was one of the original hybrid engines Miller had built in December 1943. The engine that had flown the test flight. The engine that had proven hybrid methodology worked. It had been removed from service in 1946, stored forgotten for 7 decades. The historians examined it. They found Miller's hand-machined connecting rods still perfectly balanced. They found the British Hurricane supercharger bearings adapted with aluminum sleeves that showed microscopic precision. They found evidence of repairs and modifications made in the field using improvised tools. The engine was a masterpiece of practical engineering. The museum decided to restore it for display. During restoration, conservators discovered something unexpected. Scratched into the inside of the crankcase, invisible unless you disassembled the engine completely, was a message in Miller's handwriting. If you're reading this, it means this engine lasted long enough for someone to care. I hope it kept some crew alive. RM 12-2743. Miller had left a message for the future. A message that assumed his work would outlast him. A message that hoped, even if nobody remembered his name, the engines would do what they were built to do, keep crews alive. That message encapsulates everything about Robert Miller. He didn't work for glory or recognition. He worked because aircraft needed to fly and men needed to come home. The fame, the awards, the historical recognition, none of it mattered to him as much as the simple satisfaction of seeing bombers lift off the runway powered by engines everyone said were impossible. The museum now displays that engine with a plaque explaining Miller's story. Thousands of visitors see it every year. Most walk past more interested in the fighters and bombers. But some stop. Some read the story. Some mechanics, some engineers, some people who understand what it means to look at a broken thing and see how to make it whole. And those people leave understanding that the greatest innovations often come not from laboratories or universities or corporate research departments, but from ordinary people with extraordinary determination who refused to accept impossible as an answer. From a Detroit auto mechanic with a crazy idea to a methodology that changed military aviation forever, Robert Miller proved that expertise matters less than persistence, that credentials matter less than competence, and that one person who refuses to quit can accomplish more than 1,000 experts who never try. Because of him, 1,800 American airmen who should have died came home. Because of him, 342 aircraft that should have been scrap flew thousands of combat missions. Because of him, mechanics around the world learned that impossible just means nobody's figured it out yet. That's the power of refusing to accept failure. That's the legacy of a man who turned junk into flying fortresses with nothing but a wrench of vision, and the absolute conviction that if you measure carefully enough, machine precisely enough, and believe completely enough, you can make anything work. Miller died quietly in 1971, mostly forgotten. But every time an aircraft receives field maintenance instead of being grounded for factory service, every time a mechanic improvises a repair that technically violates regulations but keeps something flying, every time someone looks at a broken machine and says, "I can fix this," Robert Miller lives. His name might fade from history books. His face might be forgotten. But his refusal to accept impossible, his proof that ordinary people can do extraordinary things, his legacy of keeping aircraft flying and bringing people home that never dies. That's forever. They flew, and that's all that mattered.